All right, so a lot of questions in the chat, a lot of questions by email, all of them pretty much for organic. So we'll start working through the email questions first. State packet. On page 10 of the studying packet, the last problem with HCl and light flow, so it's 4 different products formed on the answer key. Generally, when doing this problem like this, would it be better to include 4? Honestly, for most of these reactions, I'm just not sure how many products I need to draw. So let's take a look at problem 10, page 10. And so we've got HCl and light. We've got bromine, and with the HCl, if we were just to add this normally, so without the peroxides there, we would end up with this compound here. So 3-chloro, 3-bromo, 3-chloropentane. And this is an A chiral molecule. You've got 2 alpha groups on the opposite sides of this chlorine bromine, so there's no need to draw anything else. But let's just add some light or some peroxide or something to give us the free radical mechanism, and we end up with this structure here. So I would say as a first pass approximation, look at it and say, okay, just draw it without any stereochemistry. And ask yourself, are there chiral centers? In this case, we have 2. So we have 2 chiral centers. This gives us 2 of the second combinations. So there are 4 stereoisomers here. The RS for the Br and the RS for the chlorine. So you would actually, this is where these 4 come from, is that we've got wedged, dashed, one wedged, one dashed, one wedged, one dashed. So this is kind of going full circle here with what we covered on the first exam, which was regarding the number of different stereoisomers. So basically the number of RS centers you would go through. So this is kind of just feeding back on that. Do you create chiral centers? And based on the reaction, how many chiral centers can you produce? Are these cis or anti-reactions? Are they stereospecific? Now, when it comes to the free radical, we're always going through a radical intermediate. Because we're going through that radical intermediate, we get both the R and the S forms. This is the challenge with alkenes, is there's really no preference for one side or the other. So if you have a reaction that's not inherently stereospecific, you're getting all possible stereoisomers. It's when we start getting into these stereospecific reactions, when we start getting into the syn and anti-additions, that's when we start cutting down the number of potential enantiomers because of the limitations of the reaction itself. Because it's stereospecific, we can't form all possible enantiomers. Next question. So I have another question with the Diels-Alder reaction, so I just wanted to ask before I forget. From previous examples, I see that when the product is formed, we're specifying the stereochemistry for the groups that are further away from the double bond. I might have interpreted that incorrectly, but why aren't we specifying the stereochemistry for the groups that are right next to the double bond? So with Diels-Alder, gotta have a better pen than that. At your most basic form, your Diels-Alder is going to form a cyclohexene ring with these 2 carbons being the ones that finish up with the double bond between them. So when we get on this side, if we have, we'll put 3 groups here, A, B, C. If A and C are trans, they have to be trans in the final product. And if 2 groups B and C here are cis in the starting product, they have to be cis in the final product. So why don't we worry about if we had like group little a and little b, why don't we specify here little a and little b? And this is actually kind of building on that discussion board I asked last week about what's more, give an example of a more stable cis isomer. Because we can never make this part, this group here and this group here trans by the reaction, as well as just if we had a cyclohexene ring, we can't contort it to make this a trans isomer. A and B will always be cis in the final product because that's the only way to generate the cyclohexene. So the reason why we don't need to specify the stereochemistry here of the A and the B groups is because they're always going to end up being cis when we're done. Now, when it comes to this group here and this group here, it's going to kind of follow the same reasoning. Well, okay. You're going to end up with a lot of stereoisomers for this as well. And I think generally what happens is the ones on top end up getting pushed back. But that's also why typically when we write these, we try to stick to very simple examples. So if you have something on the ends of these double bonds, off the top of my head, I'm not quite remembering which way they end up, but I want to say the groups that are up and down, maybe they end up both being wedged. But there is some stereochemistry associated with these as well. We're just going to typically stay away from problems that deal with this, because Diels-Alder does quickly get very complicated. All right, next question. Page 15, 16 of the state pack, what does the final part of the reaction CH3 to S do? I understand everything up to that point. Okay, so this dimethyl sulfide is a solvent. So you have, so ozonolysis proceeds through two steps. So if we have any type of double bond and we perform ozonolysis, we'll end up producing an aldehyde or a ketone. Easiest way to predict ozonolysis is you just cut through the line. This here is just a solvent that's used for decomposition. So in the first step, we end up forming an ozonide complex. This is a horribly complicated intermediate. I think it looks something like this. So that's what step one does, is it reacts with these to form the ozonide complex. And then your dimethyl sulfide here, this is going to be a solvent which is used to decompose this complex down into these. So the CH3-2S doesn't do anything in terms of the chemistries we're worried about. It's just a way to derive the decomposition part of the ozonide complex. So short answer is it's there because it's technically true. The reaction won't happen without it. Longer answer is that it's involved in the mechanism that's used for decomposing the intermediate, which is formed with the ozonide, formed with the ozone, and you have to decompose it in order to get to the final product. But first you have to make this first, which is what the first step. It makes the intermediate, and then this decomposes the intermediate back down. Page 18. Okay. So page 18, you start with this compound here, and you proceed through multiple steps. The first step is chlorination, the second is elimination, and the third is Diels-Alder. And the first time of the question, they're seeing that so far. So when you do the halogenation, this is an anti-addition. So one chlorine is going up, the other is going to go down. Doesn't really matter how you specify them. You'll end up with both enantiomers. There should be two stereoisomers here. Yeah, you'll end up with two, because this isn't a mirror image, it's not meso. You'll end up with both the R and the S form, so there'll be a 2S. You'll end up with two S's or two R complexes. So one of these is S, one of these is R. Next step is you take it around, you do the elimination, and you'll end up with this complex here. And we'll drag it back so you'll end up with the 2,3-dimethyl 1,3-cyclohexadiene. This is where it gets a little bit more complicated. So we do the Diels-Alder. And as I said, when we do the Diels-Alder, the thing we have to keep track, this is why we number the carbons. We have 1, 2, 3, 4, alpha, beta. This is alpha, this is beta, this is 1. Oop, numbered them backwards. This molecule is symmetric by design, makes the Diels-Alder product a little bit easier to predict. So we have 1, 2, 3, 4. So when you run the Diels-Alder reaction, first thing I look for is what's connected to 2 and 3. So we're going to have a methyl group here and a methyl group here. So there's your second and third carbons. But the thing is, 1 and 4 are connected. And so we have to keep that in mind, is that 1 and 4 are actually connected by this bridge. So what will happen with this Diels-Alder complex is we end up forming a two-ring complex. There's a ring here, and then there's another 6-membered ring formed from the Diels-Alder product. So we've actually got 2 fused 6-membered rings here. And that's kind of the last step. So the answer that the student gave is missing this ring. That ring is this chunk of the diene that you have to connect between carbons 1 and 4. And this is why I recommend numbering the carbons. If 1 and 4 are connected, they have to be connected when you're done. Now you'll end up, again, there's a lot of symmetry with this molecule, so this pretty much ends up being the only product when you look at all the different possibilities. Okay, now to the chat. With the following reactions: halogenation, halohydrine, potassium permanganate, hydroboration, oxidation, Diels-Alder, X2, addition to alkene, anti-Markov, Markov, Markov, Markov. The chiral center is not formed as stereochemistry is necessary. Do double dash needs to be presented. No, if you end up forming an achiral molecule, you can ignore the stereochemistry. Because chiral molecules, the stereochemistry isn't relevant. You don't have that issue of needing to specify if you got R or S, because there's no such thing. So I would say this is a good time to brush off the notes on identifying chiral centers from test 1. Look at your molecule when you get done. If it's achiral, you don't need to add anything. If it is chiral, this is where you need to know the stereochemistry of the reaction. For alkene reactions, do we need to pay attention to chiral center or no? If no chiral center isn't produced, then do we not include it in the final wedge and dash? I think it's kind of a similar question. For an alkene, if you don't form a chiral center, you don't need to worry about wedge dash. It's going to show up a lot if we have cycloalkanes, because rings inherently just kind of give you that opportunity for more stereocenters. And so I would say that's where you want to keep an eye on it. But definitely for a lot of definitely for Markov-Markov reactions of linear and branched alkenes, those typically don't produce a lot of chiral centers. So don't understand the logic for it. So many possibilities of it for reactions, and I do not look for chiral centers forming, so I do not understand what to look for. Big thing to do is take a step back and look at your final product and ask yourself, are there chiral centers? So if you looked at this molecule and said, okay, are there chiral centers when I get done? If we look at this, going left and right, there's definitely a chiral center there, because left we don't have anything, on the right we do. We have a methyl and a Cl. We end up doing the 2 chiral centers. So whereas if we did halogen addition to butene, if we look at it, this molecule, does it have 4 chiral centers? It does have 4 chiral centers. Trying to think of a situation where you wouldn't end up with a chiral center. Yeah, premature. I would always just keep an eye on it, personally. I can't think of any examples off the top of my head. That doesn't mean they don't exist. But that's why there's a lot of emphasis on the notes of the chirality of the final molecule, like describing if reactions are syn or anti, describing if they invert chemistry. This is all kind of harkening back to early exams where when you looked at like SN1, SN2, you need to know the stereochemistry of that reaction when it happens. It's building on that. All these reactions have some degree of stereospecificity. I saw an example of deals altered where no chiral centers were formed, but answers included more than one option. So not only are there stereo issues to consider, there's also constitutional isomers with things being connected in different orders. So we can definitely generate achiral deals altered products. But there's a caveat on this. So here, even though this will not generate chiral centers because you end up generating, when you get done, so let me draw the predicted product here. So we end up with this. There's no RS for anything around a double bond, but we end up with a diethyl group here and a dimethyl group here. And you say, well, okay, actually I didn't put an ethyl group in here. Okay, that's not chiral and that's not chiral. That statement is true. But if you look at the molecule, in this case, the ethyl groups are on opposite carbons. They're on opposite sides of the rings. But I arbitrarily drew this with the two ethyl groups down. I could have easily drawn this with the two ethyl groups, or drew this with two ethyl groups up. I can easily draw this with two ethyl groups down, and this will switch where the ethyl groups are in the final product. So the complication with Diels alder, and I had a student ask about it, and I said, like, the truth about Diels alder is that we have to kind of, as instructors, keep a reserve pool of easy examples as to the side for exams. Because we don't want you to end up with these nightmare scenarios where there's like dozens and dozens of final products. That said, if we've got all our easy problems on reserves for the exam, everything else that remains is a hard problem. So with Diels alder, it quickly gets complicated as to what you can produce. Because it depends on if these are both asymmetric, meaning that there's no mirror plane in them, you quickly generate scenarios where it matters how these two approach each other. Because they're both planar, it doesn't matter. As long as they're both sitting in plane with each other, you'll end up generating the Diels alder product. But even though you may form an achiral molecule, and this is an achiral molecule, there are no RS centers on it, they are constitutional isomers. We can form one where the alpha group is directly opposite the two methyl groups by using this one, or we can use this one and get a situation where this ethyl group is opposite the two other ethyl groups. So it's basically the difference between a 1,3,3 and a 1,4,4 triethyl cyclohexene. So again, Diels alder is going to get complicated really, really fast because of the fact that they are planar molecules and there's no preference for one or the other. For these alkanes, if reaction to chemical formula, we still need to include other possibilities. And yeah, I would say if it's a possibility, you need to include it. But again, don't freak out too much because the test is designed to be a lot more straightforward. There are questions that are meant to be reserved to the side. Diels alder just quickly gets complicated. How do you do ozonolysis for an alkene and a cycloalkane? So I'm thinking you meant to type cycloalkene because the cycloalkane doesn't do ozonolysis. Metathesis for a cycloalkene. So ozonolysis is the same for linear alkanes as it is for same for cyclic alkanes as it is for branched alkanes. So what we do is we draw a line through the double bond and we put an oxygen on there. And so in this case, we end up generating an aldehyde and actually end up generating two aldehydes. So in this case, you would get this ethanol and you would get propanol. So what about the one up here? Well, we're still going to break it up. But what's numbers? 2, 5, 6. But it's still a carbon chain. 1, 2, 3, 4, 5, 6. And so our double bond just does that. So what we do is we cut it and then we just stretch out the molecule. What makes cycloalkanes different than linear alkanes for ozonolysis is that instead of ending up with two free molecules, you're basically tying together the N carbons and generating a long dialdehyde or a diketone or an aldehyde ketone. Now, metathesis for cycloalkanes depends on what we're reacting it with. So one option, and you'll see this a lot, is reaction with ethylene, and we'll do the Schrock. Doesn't really matter which one you work with, Schrock or Grubbs. So the reason you would do this is what's called ring opening metathesis. So ring opening metathesis, what we do is we use ethylene to break open a ring. And all we do here is cut both of them in half and we reattach them. Well, this is symmetric. So if we look at it, this isn't going to do metathesis with itself because that's what's called ring closing metathesis, RCM. So with ring closing metathesis, we take, okay, we'll talk about it. 1, 2, 3, 4, 5, 6, 7, 8. So for ring opening metathesis, we take ethylene and basically we clip open the double bond and convert those to CH2s. So the first step here is that we're going to open up the ring a little bit. And instead of these being attached to each other, we're going to add CH2 groups so we get these two terminal alkenes, and then we just stretch it out. So that's ring opening metathesis. This is an equilibrium reaction. So you can get what's called ring closing metathesis, RCM, where you take this molecule and the two ends connect to each other, you end up forming a ring, and we start pumping the ethylene off. So this is the power of metathesis, is that if you want to create cycloalkanes from longer chain alkenes, you can definitely do that. So ring closing is where they use the formation of ethylene because ethylene is pretty volatile, and they can use that, pull off the ethylene to force the ring to close. Or if we have a cycloalkane, we can pump in a whole bunch of ethylene, and this will cause the chain to basically open up. You just cut it, stretch it out, and then add two CH groups to the end. The other option here is metathesis with yourself. So when we do this metathesis with ourselves, there's a couple ways to look at it. There's the simple, and then there's the polymerization. Now, in this class, we're going to focus on the simple. So what happens when you do metathesis with yourself is that you're going to cut this double bond, and you're going to do it twice, or you're going to do it with two molecules. So we're going to cut the ends, and we're going to attach one to there and one to there. So each of these contains 6 members, so we're going to go to a 12-member ring. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And we end up with these nice symmetric cyclic dienes. So what happens is we cut the rings open and we attach the two ends of the rings to each other, and we start building this bigger circle. Now, this is just assuming that you have a very low concentration in them and you're just trying to do that first simple metathesis. Now, what can happen is that you can make this bigger and bigger. So this can metathesize with itself. So that gives you 24, 48, 48, 96. You get this exponential growth. And this was considered ring opening metathesis polymerization, ROMP. So with ring opening metathesis polymerization, and we're not going to really step into this course, but it's kind of the extreme of this. So let's say you just keep pumping this in over a Schrock catalyst, and you keep going and going, and that ring just keeps getting bigger and bigger and bigger. Eventually, this ring will trail off to infinity. And what you'll end up getting is the polymer. And it will begin to stretch out to the point it looks like a big chain. And we would describe it this way. We would draw the brackets to say that we've got this starting unit in here being stretched out and attached to other ones just like it. And so this is the ring opening metathesis polymerization. This is part of the reason why the metathesis catalyst got the Nobel Prize, was because this is a pretty hard reaction to do if you don't have a metathesis catalyst, but you can create some really weird and unique polymers by doing this. But again, this is kind of bigger picture down the road, not something we're going to really talk about. For the simple one, if you're just going to metathesize with yourself, you're going to cut the ring open, stretch it out, and connect the two ends. You're basically just going to double the size of the ring and have double bonds on opposite sides of that. If you're just going to do what's called ring opening metathesis, this is where you would pump in ethylene. Ethylene is just going to cut these double bonds, open it up. Instead of having a linear alkane, now you've got a cyclic alkane that's stretched out, and you've added 2 carbons from the metathesis reaction. Ring closing is just the opposite of that. I don't really do ring closing metathesis. That's a little bit harder to see. But with ring closing metathesis, it's just a reverse ring opening. You've got two terminal alkenes, you run the metathesis reaction, and they basically come around, connect each other, and you get this ring. This is another one. We tend, at this level, stick to very simple examples of this. You can definitely conceive of far harder examples. A lot of metathesis actually shows up in pharmaceutical chemistry. Both alkene metathesis, ketone metathesis, that's the Wittig reagent. There's a lot of metathesis reactions that end up going on. They're all kind of the same flavor, which is why we're giving an introduction to them, but those biopharmaceutical molecules are incredibly complicated. We don't want to work with anything that strange. And actually, if any of you have looked up the structure of the Schrock and Grubbs catalyst, they are very complicated molecules, which is why we just write Schrock or Grubbs. And there's different generations of those catalysts too. So that's it for the questions I got asked. So what I'm going to do is I'm going to drop it to just the standby screen. I got a unrelated questions getting popped up to me in another chat. So again, if you got questions, post them to the chat. Otherwise, and I have no idea what happened to the live stream for tomorrow. Apparently, I'm doing that right now. We'll see. Anyway, I'm here if you got questions. All right, that seems to be it for questions today. So again, if you have questions, these are not lessons, these are lectures, these are very much office hours, so please feel free to email in advance, and I will see you all tomorrow.